Well, this is section 5.3, Graphs of Polynomial Functions. Some of the stuff here is new, some of it is review, so we'll just get started and see what's what. So recall that the graph of a polynomial function is both smooth and continuous. And so if we're trying to identify which of these are polynomials, this one is a polynomial because notice it's smooth, it has no sharp curves or corners, and there are no breaks in the graph. So this is a polynomial. This is not a polynomial. And the reason is because of this sharp corner. So this is not a smooth graph. Okay, so not a polynomial. This graph is a polynomial, again, smooth and continuous. And then here you see a break in the graph, and that means it's not continuous. Right, so one above was not smooth, and this one is not continuous. So this is not a polynomial. So those are two surefire ways that you can tell when there's not a polynomial in the graph. The other is just factoring to find the zeros of a polynomial. And remember that a zero is just any value of x for which f of x equals 0. And these are called, again, the zeros of the polynomials. So we're going to go ahead and factor this function. So the first thing we'll do is we're going to go ahead and set it equal to 0. And I'm going to factor out a GCF, which is going to be x squared. So I'll be left with x to the fourth minus 3x squared plus 2. And then this resulting quartic I can factor as a difference or a regular quadratic trinomial because I've got this 4-3-0 pattern or 4-2-0 pattern in the powers. So I can factor this. And I'll do that with the normal methods. I'm looking for two numbers that multiply to 2 and add to -3. And so that'll be -1 and -2. And so this will be 0 equals, can't forget that x squared, that's got to come along. So this will be x squared minus 1 and x squared minus 2. And then I can further factor this difference of squares as x minus 1, x plus 2. And then this is no longer factorable. And so here's your factored form. And once you factor it, according to the zero product property, we can actually set each of the factors equal to 0 and solve them independently, which is actually really, really handy to do. So this time I'm going to show you that long process, and afterwards I'm just going to start going straight to the zeros. So this would just be x equals 0 twice, right? Because if you have a square, you're going to end up with two roots. This would be x equals 1. This would be x equals -2. And this one we would have plus or minus the square root of 2. And so that's exactly what we would expect with a 6th degree polynomial. I'm going to expect to have 6 roots, and that's what I have here. So I actually end up with positive root 2 and negative root 2. That's two of my roots, or zeros. And then here's number 3, number 4, and then the double 0 is 5 and 6. And so those are the roots by factoring, and you can see those here indicated on the graph. Here's the negative root 2, positive root 2, there's the 1, the -1, and then 0. 0 just happens twice. You only see it once on the graph, but it does happen twice. And so factoring again, I wanted to show you this example because this is what we call factoring by grouping with 4 terms. So we're going to find the GCF of the first 2 and the second 2. We'll be left with x minus 5, and then I need to make sure that this factor is the same. So I'm going to factor out a -1, and I'll be left with x minus 5 again. And my key indicator that I'm doing this correctly is that these two factors are the same. So then I can factor this binomial out of both, and I'm left with x squared minus 1, which will factor a little bit further because that is a difference of squares, x minus 1, x plus 1, and then again jumping straight to the zeros, that's x equals 5, x equals 1, and x equals -1. 3rd degree polynomial. I do have 3 roots, and so I know that I've found them all. It's pretty easy because remember, once we want to find, let's find the x-intercepts first, and that's with f of x is equal to 0. So the cool thing is, they've already factored it for us, right? So we're just going to take all of these factors and set them equal to 0. But let's first realize that x minus 2, there are 2 of those because it's squared. And at this point, we can go ahead and just say x equals 2, x equals 2, and x equals negative 3 over 2. And there are your x-intercepts. The y-intercepts, remember, that's just f of 0. And so if we, have a 0 minus 2 squared and a 2 times 0 plus 3, that's pretty simple, right? Like that's negative 2 squared. And then 2 times 0 is 0, and then this would just be, a 3. So that'd be 4 times 3, and that is 12. So that's going to be our y-intercept. And our x-intercepts are just these, where the function is equal to 0. We love doing that from the factored form. So the next part is a new vocabulary word you probably hopefully remember from Algebra 2. And so we want to talk about zeros and their multiplicities. And graphs tend to behave differently at a different x-intercept, and that's going to be dependent on the multiplicity of that 0. And all that means is the number of times that a particular factor or 0 appears in the factored form. So if we look here, this 0 would be x equals negative 3. It occurs once, so that's multiplicity 1. X equals 2 occurs twice, so that's multiplicity 2. And x equals negative 1 occurs, thrice or 3 times. And we won't write an x, that'll be confusing. 3 times, and that's a multiplicity 3. And so whenever this happens, the graph behaves a little differently. So if we're looking at one root, that's at negative 3, it just crosses through, right? So that just crosses the x-axis. Twice, we see here at negative 1, we see that at 2, Notice it bounces. It just touches the x-axis and then turns around. So we call that a touch. And then here at 3 times, that occurs at negative 1. And so notice that we have like this cubic looking behavior. And for me, that's called a saddle point. So we have like this saddle where it kind of evens out. And so that's going to help us later in kind of looking at the graph and figuring out what its equation is. And so again, here's some more information. This is a single 0, power of 1. A 0 that has multiplicity 2 bounces off, and the 0 with multiplicity 3 does have this saddle looking behavior. So identifying zeros and their multiplicities. So the first 0 occurs at x equals negative 3. And notice here we have a touch, here we have a cross, and here we have a saddle. And I just kind of label that on the graph. So this would be at negative 1, this would be at 4. And so the possible multiplicity for negative 3 is, and we'll abbreviate multiplicity, we would say 2, because it does that bounce or touch. At negative 1, it crosses straight through, so this is multiplicity 1. And at x equals 4, we would expect a multiplicity of 3 because it does have that saddle point. And notice again, we do have 6 zeros, which we would expect with the function of degree 6, 2, 3, 6. All right, so you try, take a look at this graph and see if you can identify the zeros and their possible multiplicities, and make sure you read those instructions there that tell you that this is a function of degree 9, so you will have a total of 9 zeros. So if you want to pause the video and come back to see how you did. All right, so x equals negative 5, x equals negative 1, and x equals 3. And the multiplicity here would be, this would be a multiplicity 3, to be a multiplicity 2, and this would be a multiplicity 4. The interesting thing here is notice that instead of it just kind of bouncing, it does flatten out a little, and that does mean higher multiplicities. And so even multiplicities, just to take this a little further, even multiplicities bounce off. Odd multiplicities do this saddling behavior, and they just flatten out the higher the multiplicity. So sketching the graph of a function this is going to be really important for us. We need to use all the key features in order to figure this out. And so the first thing I want to do is make sure I've got all the zeros. And so the zeros for this function are actually going to be x equals -3, and that's multiplicity 2. X equals 5, and that's just a multiplicity of 1. And the y-intercept, which can be obtained by, f of 0 is actually going to be -45. So we'll have a intercept here at -45. I'll have a 0 at x equals 5, and I'll have a 0 at x equals -3. And just as a reminder, this multiplicity 2 at -3, this is going to be a touch, and this is going to be a cross because that's a single multiplicity. And we also need to go back and figure out the end behavior, right? So the leading coefficient is negative. And the degree of this function is 3. There's 1, 2, 3 roots. And so that means that it's an odd degree polynomial. The leading coefficient is negative, so we'll start going down. And on the left-hand side, we're going to do something different. Recall that from section 5.2. And so then we're just going to sketch the graph. It's going to be really junky, and that's okay. So that's going to be a cross. Whoops, looks like I miscalculated this. Y-intercept's going to be 90. My bad. So notice, if you ever miscalculate, your graph's not going to make sense. And that's why I wanted to show you that. So if you mess up on your intercept, your graph's not going to make sense. And now we can cross. It'll cross through this intercept. It'll bounce off. Then it'll go back up this way. So that's important. Okay, now you try. Go ahead and sketch the graph here. Give it a try. See how far you get. And for this graph, we would see something very similar to this. And so this is another new idea, and we haven't really seen this one before. This is called the intermediate value theorem. Good. And so in some cases, we might know 2 points on the graph, but not the zeros themselves. And so we know that if those 2 points are on opposite sides of the x-axis, then it has to cross the x-axis at some point because a polynomial is a smooth and continuous graph. There are no breaks. And so this red is a formal statement of the intermediate value theorem. But we can apply this theorem to the special case of graphing quadratics. And this is what we said here. So the function is positive here. It's negative here, indicating that there must be a place where it crosses the axis. So using the intermediate value theorem to show that this function has at least 2 real zeros between x minus 1 and x equals 4. So to start, we want to make a table so that we can evaluate the function at all of these integer values between the two values we want to know about. So we want to know between 1 and 4, so that's 1, 2, 3, and 4. And so evaluating the function at those values, we're going to see that this is 5, 0, -3, and 2. And so we're looking to show that there are 2 zeros. Well, here's one of them. That's done. That's number 1. But there's not another 0 that's clear, but we can show, even though we don't know exactly what it is, we can show that there is one because we can say x equals 2 is clearly a 0 of the function. Since f of 2 is equal to 0, and since f of 3 is negative, and f of 4 is positive, there must be a 0. between x equals 3 and x equals 4. And so the other really important piece that you can't leave out here is we want to insert here by the IVT. We have to cite the theorem that tells us that as justification. So if you want to give it a shot and try to see if this function has at least one zero between 1 and 2. So we would say since f of 1 negative and f of 2 positive, by IVT, there must be a 0 between x equals 1 and x equals 2. Done. Right, and then writing formulas for polynomial functions. That's pretty straightforward. We're going to solve for the a value very much like we did previously. All right, so the first thing you want to do is identify the roots. So I have roots at x equals negative 3. That'd be a multiplicity 1. I have a root at x equals 2. That's going to be a multiplicity of 2. I have a root at x equals 5, and that's a multiplicity of 1 because it crosses over. And I have a y-intercept at 0, negative 2. And so the first thing I'm going to do is write in these factors. And so that's going to be x plus 3. That'll give me that x minus 3 here. This will be x minus 2. That'll give me that positive root. It's going to be squared, multiplicity 2, and this will be x minus 5. So the only thing we're missing now is there's an a value. There's a stretch factor out front here that we have to solve for. And we're going to do that using the fact that this is x and f of x, right? You can use any other point. Just like before, I really just like using the y-intercept because it makes things more simple. This would be 2, this would be a times 3. Negative 2 squared is 4, and then times negative 5. And so this would be negative 2. 3 times 4 times negative 5 is going to be negative 60. And dividing that out, you'll get 1 over 30 for your a value, and then you just go back and plug that in here. And so your function is f of x equals 1 over 30, x plus 3, x minus 2 squared, x minus 5. So again, solving for the a value just like we've done several times before with linear functions and then quadratics. Now we're just extending it to the polynomials. If you want to give this one a try, go ahead and pause the video and give it a shot. All right, so this one you should get negative 1 over 8, x minus 2 cubed, x plus 1 squared, x minus 4. All right, then the last part of this section is using local and global extrema. And see, they're just the hills and valleys. Remember, we had a global maximum with any quadratic, but sometimes we will have these maxima and minima that may not be the largest maxima or minima because we have so many terms. And finding the values of these local maxes and mins for a higher degree polynomial, we need calculus to do that. And of course, we don't have that toolkit at our disposal. So what we will do is we will use technology by locating the location where the output values change from increasing to decreasing or vice versa, or by simply looking at a graph. And so for example number 8, it says an open top box is constructed by cutting out squares from each corner of a 14 by 20 centimeter, blah, 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 and then folding up the sides of the box. And so what we're going to do is I'm going to go ahead and draw my box. And then I'm going to cut these corners out, right? And that's how we're going to form the box. And this is 20 centimeters by 14 centimeters. And that's all the way to the ends, right? And if we say this is X and this is X, and the dimensions of the box after it's folded up is what we're looking for. So recall that volume is length times width times height. And so the length of this box will be 20 minus 2x because of the two corners. The width of this box will be 14 minus 2x. Then the height of the box will just be x because we're going to fold those corners up. And so you can see that we have a third degree polynomial here. It's going to be kind of difficult to find the max of. So what we're going to do is we're going to put that into a calculator, and then we're just going to step up until we can find it. So the table, if I multiply everything out, or you can just put it in here in the factored form. So I want to start at 0, and I want to step about 0.2, and then I just want to kind of look at the values and see when they start decreasing. So if you're looking, all the denominators are the same. We're still at 41,000, 41,900, 42, 40. Okay, and at this step, notice here, we were increasing, and now we've started to decrease back down. And so I'm going to say that my maximum occurs at approximately x equals 2.8. And so x equals 2.8 approximately. And if we wanted to write that in terms of the x versus the volume, we would just go back over to our calculator and get the output. I'll hit my toggle button. That's 330.8. So it's going to be about 331 cubic centimeters. But that x value will be 2.8, and that's going to be my maximum that's going to give me the largest volume, this right here. Okay. And you can see it represented here on the graph. It's the local maximum. So if you want to try, go ahead and plug that into your calculator. See if you can find both the maximum and minimum values between x equals -1 and 4. So if you want to pause. Right, so the minimum here would be 0, -6.5, and the maximum would be approximately 3.5, 7. So go ahead and start working on the practice problems that are posted under the problem sets, and I will see you guys in class.